Think about the first hour of your day. Your smartphone wakes you up, a coffee maker starts brewing on a schedule, and an app calculates the fastest route to work. We are surrounded by machines that seem remarkably intelligent. But there's a massive misconception hiding in plain sight. Most of the devices we interact with aren't actually thinking at all. Take a household appliance like a microwave. This is what we call automation. A microwave doesn't know what kind of food is inside or how hot you actually want it. It operates strictly on fixed timers and preset rules that a human programmed into it. The exact same logic applies to public infrastructure, like standard traffic lights. They change color at set intervals. If you give an automated system the exact same input, you will get the exact same output every single time. That rigid consistency is useful, but it creates a critical weakness. In the 1940s, a mathematician named Alan Turing asked a simple question: can machines think? At the time, computers were just massive calculators. Turing wanted to build systems that could learn from experience and adapt, rather than just crunch numbers. The modern answer to Turing's ambition is machine learning. Instead of giving a computer a rigid list of instructions for every possible scenario, programmers feed the computer raw data. Here is the difference in architecture. Automation runs on a straight line: start, execute code, stop. Machine learning operates on a continuous loop. Algorithms process data to build models, and as they process more data, those models improve over time. Artificial intelligence discovers its own insights by analyzing raw information, building internal models that reach conclusions independently of human instructions. To see how that works, look at your email inbox. How does the system know what is a normal message and what is spam? This diagram illustrates a process called supervised learning. The system is initially fed data that already contains the correct answers. Engineers provide thousands of emails that are explicitly labeled as either spam or not spam. The model analyzes those examples to learn the relationship between the inputs, like specific trigger words, and their labels. Once trained, it can look at a brand new, unseen email and accurately predict which category it belongs to. Supervised learning is like a student studying a teacher's completed answer key before sitting down to take the final exam. But what if you don't have the answers in advance? How does an online storefront recommend exactly what you want to buy without ever asking your preferences? This diagram shows a different approach: unsupervised learning. Here, the algorithm receives a massive pile of raw data, like browsing history, your click rates, and purchase times, without any labels attached. The model scans this raw information to find hidden similarities on its own. It autonomously groups users into distinct clusters based on their behavior, separating the casual browsers from frequent buyers. Without a single human providing guidance, unsupervised learning takes chaotic information and turns it into highly organized, predictable consumer profiles. Recommending products is one thing, but how does a machine navigate a constantly changing, highly unpredictable environment like a busy highway? This requires extreme trial and error. This chart lays out the mechanics of reinforcement learning. The system operates in a loop. The agent, the software making the decisions, takes an action in the environment. If it stays in its lane, it receives a digital reward. If it swerves or hits an obstacle, it receives a penalty. By continuously adjusting its strategy to maximize that digital reward, the machine essentially teaches itself how to survive and win in completely chaotic environments. You can now look around your home and accurately divide the machines into two camps: the automated tools following strict rules, and the AI systems actively learning from their surroundings. But that ability to learn exposes the core vulnerability of all AI. Its intelligence is dependent on the quality of the data it consumes. The influence of machine learning scales from simple digital filters into life-altering physical decisions: banking systems evaluating loan eligibility, security cameras scanning faces for access, and healthcare tools planning patient treatments. This introduces the danger of AI bias. If we feed a machine learning model data that is flawed, prejudiced, or incomplete, the model will learn those human prejudices. It will group, predict, and make discriminatory decisions based entirely on bad information. When a standard automated machine breaks, it usually just stops working. But when an artificial intelligence learns from bad data, It doesn't stop. It confidently makes the wrong choice. Every digital footprint we leave, the photos we upload, the text we send, and the feedback we provide, serves as the training data that shapes these models. Because these machines learn by observing our collective behavior, the ethical quality of our own digital interactions determines whether the systems of the future become biased or fair.